So we've been looking at these matrix products, these weird generalized matrix products, but it was maybe a little bit ad hoc to simply replace the sum with the min and the product with the sum. Yeah? And there is a intellectual Überbau for that, and that is the one of the algebraic path problem. So we've seen empirically that we have one basic algorithm which specializes to solving many different problems by using different operations. In fact, these form semirings. Now, I'm not a mathematician and I've not heard about these things before I studied these path problems in more detail. But actually the language I think is more scary than the actual math here. So let's look at these terms. So there is the notion of a monoid, which I think comes from the French literature. And this is my cue to show, well, this English version of the book, which I bought secondhand. It arrived a little bit wet. This book by Gondron and Menou, it is much cited, and it's one of these island books, worth their weight in gold. And it has the solutions to many problems that people would like to solve, just they don't know that it's in this book. Yeah. So, for example, if you are interested in solving shortest path problems where you have gains, so as your product enters an edge, it may gain, it may multiply, or it may be reduced. Or you can have discounted path problems where the longer you walk, the cheaper an edge becomes from your point of view. And this set of ideas and algorithms tells you how to solve all these problems. So really fantastic source. Okay, so a monoid is defined here as a tuple. We have a set of numbers. For example, the non-negative real numbers and infinity. Such a set, then there is a binary operation, and then there is a identity or neutral element, such that here we have associativity, A operator B, parentheses, operator C is the same as the thing on the right hand side, and we have always, we must have one neutral element, so that if we let our operator act on some element A of the set and the neutral element, then we just get out the member of the set A that we picked. Sometimes we need a commutative monoid, which means that A operand B is the same as vice versa. Good. Now, a semiring is given by a set and then two binary operators with their respective elements, such that we have for this generalized summation a commutative monoid with an identity element which is here called a 0 bar, and for the generalized multiplication we have another monoid with its own identity element. We need that this generalized product distributes over the summation, and you see here at the bottom what this means. And yeah, we have that this identity element for the summation is an annihilator for the product. Sometimes we need commutative semirings, which means that the order of multiplication can be reversed. If we, in addition, had an additive inverse, then we would have a ring rather than a semiring. And some people use the notion of semiring and dioid just as equivalent terms. Sometimes a slight distinction is made. But anyway, you see here the definition of a monoid and of a semiring. And if you ever hear about a dioid, then in the heads of many people, it's just the same thing as a semiring. Okay, and well, this works for sets whose elements are just numbers. It also works for square matrices. So, for example, if we have this generalized addition of matrices A and B, and we look at element ij, this is the same as generalized addition of the elements ij of the matrices A and B. Okay, and here, by the way, we have this generalized matrix product. So we have here a generalized summation, and here the generalized product. So the conventional matrix summation would just be sum over k, aik, and then the product would be our conventional product. So this would be the standard matrix multiplication in the sum product semiring. But if we now, for example, move to the min sum semiring, then we would replace the summation by the minimum, and we would replace the product by the summation. Okay, so the generalized matrix products that we have studied in the previous slot of the lecture before the break, this is what it was. Okay, all could be written in terms of this formula, just using different semirings. And now, what is the algebraic path problem? It is the following. We are looking for a distance matrix D. In particular, we're looking at the distance between a source S and a target T. And now we consider all paths, capital P, so P tilde ST, or this P script ST, this one here, this is the set of all paths that go from S to T in a graph. This capital P is one particular member of this family. So this capital P will be one path from S to T. Now, along such a particular path, we consider the edge weights along this path, and we aggregate these edge weights along the path using this generalized product. So this is aggregation of edge weights along some path P. And well, why would you have a product here? Remember the random walker. If the random walker has a finite probability of transitioning one edge and a finite probability of transitioning the next edge and so on, as we walk along this path, we need to multiply these probabilities. And this is why here we use this, or this is a Eselsbrücke, a reminder of why we actually have a product here. And this one here it sums the costs over different paths. So we have some source S, we have some target T, we have multiple paths that may or may not coincide for part of the way. For each path, we get a cost, Now the question is, how do we combine these costs from different paths? Well, and if we are, for example, interested in the shortest path problem, then we're just interested in the shortest path. We don't care about the others. So for the shortest path problem, well, we would make this one here a minimum operation. And for the shortest path problem, you know that we sum up the edge costs along the path. So for the shortest path, this would be the sum operator. So we would say that for the shortest path, we solve the algebraic path problem in the min-sum semiring. Or if we look at the definition up there, then actually we would need to specify, let's do this more completely. So the short way of calling a semiring is just we work in the min-sum, and that's it. Now the proper name, if we look at this, is to say, for example, we are looking at, let's say, unweighted, undirected edge-weighted graph with non-negative edge weights, but the missing edges we're going to code with the plus infinity here. So this is the set that we're working on. Then we have the generalized addition, which here would be the minimum operation. Then we have the generalized product, which would be the summation operation, or I could just write a plus, I could just write a plus here. And then we need the neutral elements. The neutral element for the min is plus infinity. So if I take the minimum of anything and plus infinity, then it will always be the anything, which is the minimum. And the neutral element for the generalized product, which is a summation, is a 0. So if I have some number and I add 0, then I get out the same number. So this would be like, the thing I wrote on the top would be the first name of this shortest path semiring, and the thing on the bottom is its first name, middle name, last name, and the proper way to call this thing. All right. So this here would be the standard shortest path semiring. All right, so the thing in the box is the algebraic path problem. And something to remember, so we aggregate costs along a path and then we sum costs over paths. And now we have all these possible different choices for what generalized summation do we want to use and what generalized product do we want to use. And here I give you a table from this beautiful book by Gondron and Menou. And we have here the set, then we have the generalized summation, we have the generalized multiplication, we have the respective neutral elements, and we have a comment of what this is called or what problem does it solve. So let's look at a few of these. If the elements in the set are 0 or 1 or equivalently false and true, I can use operations of max and min, or of the logical operators or and with these neutral elements, and that gives me that solves problems of connectivity, which earlier today I called percolation or existence of a path. This is also sometimes called the Boolean semiring. Then these are really cool semirings here in natural language processing. So these are, for example, all the words that you can generate from a finite alphabet. I'm not going to talk about it now, but I'm going to talk about this one here. If we use the min and the max, or the minimax path, well, this gives us, as you see, the minimum spanning tree, or it gives us the widest path, and it's sometimes called the bottleneck semiring or the minimum spanning tree semiring, and it has other names. This is the one that we will or have talked about most, the min-sum semiring or shortest path semiring. This is super important, and this is also known as the tropical semiring, in the honor of a Brazilian mathematician, hence tropical, who worked on this. There is the practically identical semiring, just not the min-sum, but the max-sum semiring, which is, like its mirror image, which is hence sometimes called the Arctic semiring, as the opposite of the tropic. This is also called the max-plus algebra or the max-sum algebra, and it has been, discovered and rediscovered in many fields because it is such an essential mathematical structure. Then we have another class of semirings, namely these are the normal operations, the sum and the product that we normally use. And these can be used to count paths, so how many paths are there between S and T, or to compute probabilities of transitioning from S and T, so to study diffusion, and this is also called the arithmetic semiring. And well, actually this is a short version. There is another book which I would like to recommend as complementary to Gondron and Menou. So Gondron and Menou is really strong on the math, and they do occasionally give practical examples of what these algorithms can use. And for being such a profound mathematical book, it's actually very readable. Yeah? So I would say this is accessible to mortal beings. This not book, more pamphlet, is also very good. It is not as deep in the math, but it gives a really nice set of application examples in different semirings. And it studies in detail, for example, problems such as the trust, various versions of the trust semiring. So here you see that the sets are not composed of single numbers, but of pairs of numbers. And one possible interpretation that you can give to these pairs of numbers is that you are trying to, let's say you're in a social network, and you're trying to aggregate information. And you have various sources of information, and so those are your neighbors in your social network, your neighboring nodes, and they again have neighbors from which they can gather information and so on. But these neighbors, or all these nodes, have on the one hand different degrees of expertise. So how competent do you think are they in assessing a situation? And then there is the other question of how much do you trust these sources? So you may know that somebody is super well informed, but maybe not necessarily willing to share the honest information with you. That would be one extreme. Or another extreme would be a really close pal of yours. You completely trust that person. The person would never ever lie to you, but unfortunately the person has no clue whatsoever. Happens in real life. And now you're surrounded by various such characters who again are connected to various such characters. And the question is, how do you weigh, how do you aggregate the information that they bring in? And here I've couched this in terms of friends, but you could couch this in terms of sensors. So let's say you have various sensing devices. They may be more or less accurate in their measurements, but the line connecting you to these sensors may be more or less reliable, for example. And this is a kind of problem that can be solved in a trust path semiring. Or you can look at the length of shortest path, the number of shortest paths, and various other things. A really interesting one is also this log sum X semiring, which is connected to conditional random fields. All right, so this is a treasure trove. There is an enormous variety of problems inside computer vision and outside computer vision that boil down to being some kind of path problem. So for example here, bridge, just one last example. This one allows you to find the bridges in a graph, so edges which, if you did remove them, would disconnect various subcomponents of your graph. Or similarly, cut vertices are vertices that if you remove them from the graph, then you will have one more connected component in your graph. So an enormous number of problems at their heart are some kind of shortest path problem, but not shortest path in the traditional sense of you're looking for the cheapest path and its cost is given by the sum of the edge weights. That would be the min-sum semiring. Yeah? So the classical shortest path stuff is just this line here in the table. And then you have all these other semirings that allow you to study other relevant problems. And for the ones listed here, there are more, some of these semirings admit more efficient solutions than others, but all of these problems here can be solved pretty efficiently. Yeah? So I would say super relevant body of theory. My summary: an enormous body of problems and models can be abstracted into the algebraic path problem. I recommend you this source, and for those who want to go deeper, I recommend Gondron and Menou. This is a later book by them. The older one is called Graphs and Algorithms. Great. So here and ask for your questions.